Hello and welcome to Tutorial 2. Our topic today is expressing uncertainty. More specifically, we're going to be covering significant figures. I'll write up here sig figs. We will talk about how to round numbers off. So I'll write up here rounding. And we'll learn how to express our numbers in scientific notation. Finally, we're also going to talk about how to convert between units using a very systematic method called dimensional analysis. So just a quick reminder before we get started with all that the notes to accompany this tutorial video are available online through my website. And with that said, let's go ahead and erase here and get started. All right, some numbers are exact numbers, meaning that they are indefinitely precise. Let's write that up here, exact numbers. All of those metric conversions that we talked about in tutorial number 1 are exact. So let's write up here, all metric conversions are exact. So if you say that there are 1,000 grams in 1 kilogram, what you're really saying is that there are 1,000.0, where that 0 is repeating on forever, grams to 1.0, again repeating 0, kilograms. We don't have to write it that way because we know that all those metric conversions are exact, indefinitely precise. Also, all counted numbers are exact. Okay, so if you walk into a classroom and you count the number of students sitting in desk, let's say there's 24 students, we would know that that's an exact number. It's not 24 plus or minus 2, it's 24 students exactly. You counted it. But some numbers are inexact, meaning they are not indefinitely precise. They contain some uncertainty. So let's write inexact numbers. Up here, all of your measured quantities are inexact. All of the measurements that you make will contain some degree of estimation depending on the measuring device that you're using. And so therefore, they have some degree of uncertainty and they are inexact numbers. So it's very important when you're recording a measurement that you record that measurement in such a way that you are reflecting the precision of your instrument, the precision of the instrument that you use to make that measurement. And we do this by recording all of the digits that are known with certainty plus one additional estimated digit. Okay, so let's talk a little bit more about that and look at some examples. Okay, so for our first example, let's consider a large graduated cylinder, maybe a 25 milliliter graduated cylinder. That's usually considered your large graduated cylinder in an introductory chemistry class. Okay, so I'll write large graduated cylinder. I'm going to draw a picture here to represent that large graduated cylinder. And your large graduated cylinder is going to have increments measured off for every whole milliliter. So I'm not going to make 25 tick marks here. I'll just go ahead and make one for 15, 16, 17, 18, 19, and 20 milliliters. Okay, so I'll just measure off a few tick marks on your large graduated cylinder. Okay, so let's say that we wanted to measure a volume of water. Now when you put water into your graduated cylinder, it's going to form a concave shape. We call that a meniscus, and you always want to measure to the base of that meniscus. So that's why I'm going to draw the water level, which I'll go ahead and draw in blue. Make it stand out a little bit more. So I'm going to draw it with a slight curve, okay? So we want to measure to the base, put a little dotted line here. I want to measure to the base of that meniscus. All right, so when we're reading the water level from this graduated cylinder, we can tell that the water level falls between, let's see, 15, 16, 17, somewhere between the 17 milliliter line and the 18 milliliter line. Remember, we're measuring from the base of the meniscus. Okay, so it's somewhere between that 17 and 18 milliliter increment lines. So we can say 17 with certainty. It's not to the 18, it's below the 18, but it's over the 17. So it's 17 point something. The 17 part is certain. Now we're going to estimate one additional digit, which is going to be out to the 10th of the milliliter, and that's going to be our estimated digit. That's based on the precision of our graduated cylinder, which only had increments to the whole milliliter. So we're going to estimate to the 10th. So some people might look at this and say, well, it looks like it's a little bit closer to the 17, so I'm going to call that 17.4 milliliters. Don't forget your units. Someone else might think it's 17.5. That's okay, because that last digit, the 10th of the milliliter, is your estimated digit. So it's acceptable that your lab partner might argue that it's 17.5 and you say it's 17.4. Hopefully you'll come to a consensus there and decide what to call it. We'll go ahead and call it 17.4 milliliters. Okay. Now this measurement, let's go back to the blue here, we would say has 1, 2, 3. 3 significant figures. Let me write here 3 sig figs, and the estimated digit is that last digit, which is in the 10th of a milliliter. Okay. All right. Now let's go ahead and use the green here. Let's say that we had this, well, let's erase this part so we can just do it all over again. Let's say that we had a water level that looked like it was right on the 17. Okay, so the base of our meniscus is going to be right on the 17. Okay. When I draw my little dotted line over here, let's say it looks like it lines up right with the 17. Okay. So you might be tempted to just call that 17 milliliters. If you did that, you would not be expressing the precision of this measuring device correctly. You would be expressing that you couldn't tell the 1 decimal place with certainty, that was the uncertain digit, the estimated digit. Therefore, this could be anywhere between 16 and 18 milliliters because the 1 place you're expressing as being the estimated digit, and that's not correct. So in order to make this correct, make sure that if it looks like it lines up directly on the 17, that you're reporting 17.0. That 0 is very important. That tells you that you could measure the 17 with certainty. There's an increment for 17 on the graduated cylinder, and that you estimated the 0.0. You had to estimate out to the 10th. There were no increments for tenths. All right, so let's do the same thing, but now let's draw a small graduated cylinder. And I think I can squeak it in right here. Make it smaller. small graduated cylinder is probably going to be a 10 milliliter graduated cylinder. Now your small graduated cylinder is going to have increments out to the 10th of a milliliter. So it has a little more precision than the large graduated cylinder, which only had increments measured off for whole milliliters. So let's go ahead and just mark off from 5 milliliters, which would be 5.0, up to 6.0. So there's going to be an increment for 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, 5.7, 5.8, 5.9, and 6.0. That one's kind of ugly there, but hopefully you get the idea. All right, so if we wanted to measure a volume of water from this small graduated cylinder where the increments go out to the 10th of a milliliter, then we're going to go ahead and estimate one digit further. We're going to be estimating out to the 100th in this case. Okay, so let's make our little concave meniscus shape here. Okay, and I'm going to do a little dot, dot, dot across because we're measuring from the base here. Okay. All right, so we can see that the water level lies between these two increments here. So this is 5.0, 5.1, 5.2, 5.3, 5.4, 5.5, and 5.6. Okay. Lies somewhere between 5.5 and 5.6. So we can say 5.5 with certainty. It's definitely above the 5.5, but it is not above the 5.6. So it's 5.5 something. So that last digit, which is going to be your 100th of a milliliter, is going to be your estimated digit. Now I think it looks pretty much halfway between those two, so I'm going to go ahead and estimate that as a 5.55. And don't forget your units, milliliters. Okay. So this measurement here has 1, 2, 3, 3 significant figures. I'll just write 3 sig figs. And the estimated digit is in the 100th decimal place. So that last 5 is the estimated digit. Okay. All right, so let's go ahead and move on to the next slide, which is slide 4, where we cover the rules for counting significant figures. It may seem pretty straightforward so far, like how we just counted 1, 2, 3, and we called it 3 significant figures. However, it can be a little bit confusing when you have zeros in your number. Okay, let's erase all this. One more quick note before I erase that small graduated cylinder. Some small graduated cylinders might have increments for every 2/10 instead of every 1/10. So be careful about that. Check your small graduated cylinder and make sure that you know whether or not it has increments for every 1/10, like what I've drawn here, or if its increments are measured off in every 2/10, which means it would only have 5.0, 5.2, 5.4, 5.6, 5.8, and then 6.0. You want to make sure that when you're counting those increments, you're counting them correctly and that you're not counting a 1/10 when it's really representing a 2/10. Okay? So just a little side note there. All right, so there are 5 rules that I have written down on slide 4. For counting significant figures. And I'm just going to write sig figs. Okay. So I'm going to read those rules and I'm going to write examples for each of those rules, but I'm not going to write the entire rule out. I'm hoping you have that in front of you already, and that would take up way too much time. All right, so rule number 1. It's probably the easiest rule of all. all non-zero digits are significant. Pretty simple, okay? So if you have a number like 282 grams, then that number has 3 significant figures. Okay. All right, rule number 2. Zeros that fall between non-zero digits are also significant. So that one's not too bad. If you have a number like 1.008 grams, okay, well those zeros fall between non-zero digits, so you're going to count them. So it's 1, 2, 3, 4. You've got a number with 4 significant figures. Okay. All right, rule number 3. Zeros to the left of a non-zero digit are not significant. They're actually just placeholders depending upon what unit it is that you have chosen to use to represent that measurement. Okay, so if you have a number like 0.0021 grams, these leading zeros are not significant. So we would just count 1, 2, so it would be 2 sig figs. And to kind of prove to you what I meant when I said that they're just placeholders depending on the unit that you have chosen to represent that number in, let's go ahead and convert this into milligrams, okay? So if I wanted to express the same number, but I want to express it in milligrams instead, in 1 gram, there are 1,000 milligrams. And if you're not really sure about this setup here, we're going to cover dimensional analysis in just a moment. So don't worry too much about this problem that I'm throwing in here right now. I'm worried more about the sig figs, which is the point right now. So I'm going to multiply by 1,000. So this number is going to be 2.1 milligrams. Notice now that I'm expressing this number in milligrams, I no longer have a need for these leading zeros because a milligram is a much tinier unit. Okay, so 2.1 milligrams, same number, just expressed with a different unit. So it couldn't possibly be a more precise measurement. Still only has to have 2 sig figs. Okay, can only have 2 sig figs still. So still 2 sig figs. I'm going to put a little arrow because that correlated back up there to that problem we did before. All right, rule number 4. Zeros at the end of a number, but to the right of a decimal place, are significant. They are assumed to be measured numbers. Okay, so if we had a number like 2.200, let's make it grams again. Okay. Those zeros that came at the end of the number would be counted as significant figures. And that's because, remember, your last recorded digit in a measurement is always the digit you estimated. So you definitely measured that, right? You estimated that last digit. So even if it's a 0, it's a significant figure. Okay, so this has 1, 2, 3, 4. 4 sig figs. All right, last but not least, rule number 5. When a number ends in zeros but contains no decimal place, the zeros may or may not be significant. Don't you love that ambiguity there? But fortunately, we have a way to make it very clear. And how we do that is that we always convert those kinds of numbers that end in zeros but contain no decimal places, we always convert those into scientific notation. Okay, so let me give you an example here. Let's say that you had a number like 7,000 kilograms. Well, that would be very ambiguous. Those zeros may or may not be significant. Okay, so this could be 1 sig fig, could be 2, could be 3, or it could be 4. As written, we don't know. So we're going to always use scientific notation or exponential notation, another word for that, scientific notation, to clarify. Okay. All right, so let's say that we made this measurement and we really wanted to express that all of those zeros were in fact significant. What we would do there is we would take this number and grab the decimal place that's at the end of the number but currently not being written, and we would move it until we got a number that was between 1 and 10. Okay, so I'm going to write 7.000 because we're trying to express that all those zeros are significant for this example. And then we would multiply that number times 10 to the appropriate exponent. And the exponent is just however many times you moved that decimal place. In this case, we moved it to the left, okay? We moved it 1, 2, 3 places. So we're going to make it a positive 3. And don't forget your units. Your units are kilograms. Okay, so now you can see that this number follows rule number 4 in that the zeros now follow a decimal place. And so clearly, this number is 4 significant figures. So let's write here, 4 sig figs. Okay. Now, if you had a number that was smaller than 1, like let's say that you were trying to express this number here in scientific notation. Let's go ahead and do that over here before we move on. Then you're grabbing that decimal place, and let's do that in a different color here. You're still going to move it until you get a number between 1 and 10. 1, 2, 3. Okay, so we get 2.1. Yeah, let's go back to the black pen. Okay, and we're going to times it by 10 to the appropriate exponent. Now in this case, you moved it 1, 2, 3 as well, but you moved it to the right. So we're talking about a tiny number, a number that was less than 1, as opposed to down here where we had a big number, a number that was bigger than 1. So our exponent, when you move the decimal place to the right, when you have a small number, okay, you're always going to have a negative exponent. So this is going to be a negative 3 grams here. Okay, so that's how you convert a number into scientific notation. A big number or a number that's, greater than 1. Okay, so you're moving the decimal place to the left, so it's going to be a positive exponent. And then a little number, a number that's less than 1. So we're having to move our decimal place to the right, and therefore our exponent's a negative exponent to reflect that small number. All right, so let's go on to slide 6, significant figures in calculations. Okay, so we are going to go ahead and cover both slide 6 and slide 7. We're going to talk about significant figures in calculations. And we're going to talk about rounding. So when we make measurements in the lab, we're usually making those measurements so that we can use them in calculations. And so you not only need to be able to round your measurements to the correct number of significant figures, but you also need to know how to round your final answers from calculations to the correct number of significant figures. And there are 2 rules that you will need to know in order to do this correctly. The first is for when you are multiplying or dividing. And the rule for when you are multiplying and dividing numbers together is that your final answer should contain the same number of significant figures as there are in the measurement with the fewest significant figures. So let's take a look at an example. Let's say that we wanted to calculate the volume of a block, and we were given the measured length as 10.0 centimeters and the width as, let's say, 5.6 centimeters and the height as 2.8 centimeters. Okay, just making up some numbers there. All right, so we're going to use the formula length times width times height and plug in these numbers. So 10.0 centimeters times 5.6 centimeters times 2.8 centimeters. And I'm going to go ahead and use my calculator for this. Okay, so 10, 5.6, and the 2.8. All right, now your calculator is not going to give you the correct number of significant figures, or if it does, it is only by coincidence. So the calculator does not know how to account for significant figures. You have to do that yourself. So I'm going to write down everything that the calculator gives me here. 156.8 centimeters cubed, because it's centimeters times centimeters times centimeters. All right, so I know that I am limited to the same number of significant figures as there are in the measurement with the fewest. So let's go back to our measurements here. Our first measurement had 1, 2, 3. 3 sig figs. Our second measurement had 2 sig figs. And our measurement for the height also had 2. Okay, so our final answer then is going to be limited to 2 significant figures. So I'm going to round this number off to 2 sig figs. In order to do that properly, I first need to look at the leftmost digit to be dropped. If the leftmost digit to be dropped is greater than or equal to 5, like it is here, it's a 6, then I'm going to round up. So I'm going to round this 5 up. If that number were less than 5, then I would round down. Okay, but we already said it's greater than 5, it's a 6, and so we're going to be rounding this 5 up to a 6. So let's go ahead and do that. So it's 160 centimeters cubed. But that 0 is ambiguous. So we need to express this final answer in scientific notation so we can clearly, unambiguously show 2 significant figures. So I'm going to grab my decimal point and I'm going to move it over until I get a number between 1 and 10. So I'm going to move it over here. So like that. So 1.6 times 10, I moved it 2 places to the left there, so times 10 to the 2 centimeters cubed. And there's my final answer for the volume of that block, expressed unambiguously to 2 significant figures. Okay, what about when we are adding and subtracting? There is a different rule to follow. When you are adding and subtracting numbers, your final answer should contain the same number of decimal places as there are in the measurement with the fewest decimal places. So let's say, for an example, that we are adding 3 lengths together. We'll just pick some numbers. Let's say 10.02 meters and 2.1 meters and let's see, 2.2 meters. Okay, so we'll add these together and we'll find a longer distance. And we don't need our calculator here. We'll just do this really quickly. We've got a 2 and we've got a 3. There's our decimal point. There's 4 and there's 1. So 14.32, and it's just meters here because you're not multiplying, you're just adding these lengths together. All right, so we just learned that when we are adding or subtracting, our final answer will be limited to the same number of decimal places as there are in the measurement with the fewest decimal places. So let's take a look here at what we have. In our first measurement goes out to the 100th. Our second measurement goes out to the 10th. Our third measurement also goes out to the 10th. That means that we are limited to the 10th decimal place for our final answer. We need to round it off to show just out to the 10th decimal place. So I'm going to write a little note here. So we are limited to the 10th because of these two measurements here. All right, so look at the leftmost digit to be dropped. In this case, it is less than 5. So we are going to round down. Okay, so our final answer, let's go back to the black pen here. Our final answer will be 14.3 meters, and I'll circle that. Okay. So it's very common for introductory chemistry students to just remember the rule for multiplying and dividing and completely forget about the rule for adding and subtracting, and then they just apply the rule for multiplication and division everywhere. And then they end up getting problems wrong that way on the test. So do be very, very careful. Make sure that you understand how to use each rule separately. And sometimes you'll come across problems where you need to apply both rules. So there will be equations that involve both multiplying and dividing and adding and subtracting. So in those problems, again, make sure that you're applying those rules separately. All right. So let's go ahead and move on to slide number 8, our last slide, and talk about dimensional analysis. Okay, dimensional analysis, also known as the factor labeled method. Dimensional analysis is a method that we use to systematically solve problems when we want to convert from one set of given units into a different unit. And the basis of dimensional analysis is the use of a conversion factor. And a conversion factor is just a fraction where the numerator and the denominator are the same quantity but expressed in a different unit. So let's just use one of our metric to metric conversions as an example. If we wanted to write a conversion factor to show how kilograms related to grams, we could say that there's 1 kilogram to 1,000 grams. Or you could write it the other way. That would be okay too. We're just showing the conversion factor of how grams are related to kilograms. Okay. But then when you go to set up your problem with dimensional analysis, you're going to set the conversion factor up such that the given unit will cancel out and your desired unit will not cancel out. Okay. Your given unit, you want that to cancel, so you're going to set up your conversion factor so that one is in the numerator and one is in the denominator, and they cancel out. And your desired unit, the one you're trying to convert into, that's going to be the one that doesn't cancel, which means that your final answer will be expressed in the desired unit. Okay, so let's do an example here, just so that I can show you this method with some numbers. I don't usually like to work a lot of problems in my tutorials. I save that for the problem set, but we'll go ahead and just do one here in the tutorial. Okay, so kind of a fun one. Let's take the distance of a marathon in kilometers, which is about 42 kilometers. Okay, and let's convert that into miles. We're more familiar with miles, so let's convert it into something that maybe is more relevant for us. Okay, so you may not know the conversion factor to convert between kilometers and miles. That's okay. You can look it up. You can look all these conversion factors up very easily, even with just a Google search or in your textbook. But if your instructor wants you to know it, make sure you memorize it. Okay, so I've already looked it up. Okay, so I know that in 1 mile, there's 1.609 kilometers. Okay, and you can write it either way for now because we haven't set up a problem, so we're not really sure how we're going to write the conversion factor. So just know you can write it either way at this point. Now we go to set up our problem. Now it's going to be important which way you write it. Okay, so we want to set this up so that the kilometers cancel out and the miles do not. So we want the kilometers on the bottom and we want the mile on top. So see how my kilometers cancel out? Okay, so grab your calculator, and 42 divided by 1.609. I'm going to go ahead and write the whole number given by my calculator. Remember, your calculator is not going to round your sig figs for you, okay? So we'll go ahead and go through that as a separate step. So my calculator gives me 26.103.16967, and that's miles. Okay, we're going to round to 2. Okay, so our final answer is 26 miles. Wow. So if you're running a marathon, you are running 26 miles. I have never ran a marathon before, but I think it's amazing that people do. Okay? All right, so that concludes our tutorial number 2. I hope that you will consider tuning in to problem set 2, where I work lots and lots and lots of examples based on the concepts that we just covered here in tutorial number 2. Thank you.